everyone, welcome. So thank you for getting up so early to come to this masterclass. So my name is Alekos. I'm from this company called 22. I'm the CEO, co-founder of this company. And our kind of mission at this company is to build open source hardware for Bitcoiners. So we have like a very specific kind of focus on making the best hardware possible for Bitcoin. And yeah, this presentation is going to be, well, it's called Making Open Source Hardware. More than teaching you how to make it, it's going to be more like my journey into building Portal, which is our hardware wallet. So yeah, it's going to be more like a looking back at the journey that brought me here with a running product. And the reason why I wanted to do this is because we love open source. So everything we do at 22 is open source. So for example, for Portal, both the hardware and software are fully accessible on GitHub. You can find the design file and the code. And we don't just want to open source the product itself, we also want to open source the process. So yeah, what I'm trying to do here is just share our process. This was my first time building hardware commercially for like a commercial product. So I'm sure it can be done better, but yeah, we believe through open source we can I don't know, we can share knowledge and we can all, let's say, improve together. So that's why I'm doing this presentation, just kind of talking, rambling a lot about our things. So yeah, how did we get here, let's say? Obviously, it all started with a vision. So what do we want to build? And the vision was, I go to a lot of meetups, especially in Italy. In Italy, we have a bit of a maybe weird Bitcoin scene that I haven't seen anywhere else. In Italy, we have a lot of regular people that come to meetups, to Bitcoin meetups, because they are passionate about Bitcoin. So they're not technical, they just kind of understand something about Bitcoin, and they understand, oh, I need to self-custody my funds, I need to keep my own keys. But they don't know how to do it because they're not technical, they don't know how to set up like a seed signer or whatever. So the vision was, speaking with those people, I kind of realized, well, we should make an hardware wallet that works really well with mobile, because those people, they don't even have laptops usually, they just have smartphones, that's the only thing they know how to use. So let's try to make something for mobile specifically. Let's make it very easy to use, because again, those people are not super technical. And let's make it open source, because again, we think not only we can all improve together with open source, it also helps with transparency. So for a customer using our product, if it's open source, they can audit, they can look into it, they can see what's going on. So that was the vision: to make an hardware wallet for mobile, easy, open source. And we considered a lot of possibilities. We ended up choosing to base our product on NFC because, well, if you want to work with mobile everywhere, so if you want to work with iOS and Android, there's not many things you can use. For example, USB devices don't really work well on iOS because Apple doesn't let you use the USB port. So it basically boils down to Bluetooth and NFC. We thought NFC was better because it doesn't need pairing, so it's like immediately ready, immediately available. It works everywhere, so again, it works on both Android and iOS equally. And the really cool thing is that it also transfers a small amount of power. So in NFC, in NFC you have like an active and a passive side, and the active side, which in this case is the smartphone, can provide power to the passive side. So usually what happens is, like even with credit cards, the reader, so the POS, powers on the credit card so that the chip inside the credit card can produce all the cryptographic signatures or whatever. And well, we figured out a cool way to use this, to just use this power to power our device. So our device doesn't have cables or batteries. We just use this small amount of power that we can get through NFC to power everything. So the microcontroller, the display, everything. Obviously, this is awesome because you don't need to carry cables with you, especially since it's optimized for mobile. So you have a smartphone, you just want to use it straight away. Also, you don't need to charge batteries. But it introduces, on the other hand, many constraints, because now you are super limited on the power you can consume. So you have to use some, especially software kind of tricks to make everything work well. Next step was what's our security model. And here, obviously, we can talk for hours about this. there's lots of different opinions, lots of different people have very strong different opinions on this. But what we tried to do was focusing on our target audience. So who are we building this for? And next question is, how can they screw up? So one example is, yeah, sure, you can come up with super secure setups with Bitcoin Core and air-gap devices, air-gap signers, whatever. But the more you increase complexity, the easier people can accidentally screw up. It gets much more likely that people just lose one piece of the key, they lose one critical piece of the whole puzzle, and then they cannot access their funds anymore. So I've seen this happen a lot. I've seen lots of people building these super secure setups, and then they even lose access to those setups. They're like so secure that they cannot spend themselves anymore because they were just kind of pursuing this absolute security. So our idea was, let's make something that is obviously secure, but also very, very easy. Because if you make things easier to use, then it's easier for people to reason about it. It's easier for people to not screw up. And one part of the security model was also how does the user interact with the hardware. And specifically, we decided to have a display and a button. It's not a clicky button, it's a capacitive button, but it acts as a button. And the reason why we did that is that we think it's very important to provide feedback to the user about what's going on. So again, what's the security model? You have a separate device that you buy to sign transaction that you create on your smartphone. So if you buy a separate device, it means you don't wanna trust your smartphone. You wanna have like a second check, like a 2FA almost kind of thing. But if this external device doesn't have a display, it cannot show you what you're signing, then you're just kind of blindly signing whatever. So you just, for example, let's take the Tap Signer, which is this credit card thing that signs Bitcoin transactions. This is super cool, but since it doesn't have a display, it's not really an hardware wallet. It's just an external key holder, let's say, external signer. But when you go sign a transaction, you just tap it and it signs whatever. So you're still fully trusting your smartphone to be showing the right thing on the display. And so this is why we decided, let's add a display and a button so the user can see what's being signed. They can press the button to confirm. And again, let's keep it super simple, so we don't have menus to navigate. We just show one very straightforward thing. We just show you the transaction. If you like it, you accept it. Otherwise, just power it off, remove the device, whatever. And initially, I also like to talk a little bit about the history of the device, so how we came to what it is now. Initially, the plan was to not have any kind of protection. So what it means was that I wanted to build a better kind of device. So you just have it, whoever has the device can spend the funds. And so the idea, the reason why I think this is cool is that you move the security, you move the problem of securing keys from a virtual abstract world, which is kind of confusing to reason about, you move it into the physical world. So then it becomes, just keep this thing safe somewhere. Just put it in a safe, put it in a drawer, hide it, whatever. But it's much easier, I think, for people, especially our target audience, so non-technical people. I think it's much easier for them to think about a physical thing to secure rather than those complex abstract models. So initially was, let's not add anything. And then I was convinced, I think it was Giacomo maybe convinced me, but some people convinced me to add some kind of extra protection on top. So now the way the device works now is you can choose. So when you initialize it, you can choose no password, we call it pair code, but it's effectively a password. So you can choose no protection, so then it becomes this kind of physical bearer object, or you can enable one, and so the flash is encrypted with this code, which means that if somebody steals the device, they cannot do anything with it. Even if they manage to extract the memory, which is pretty complicated, but theoretically can be done, the memory is still encrypted, so they cannot do anything with it. And looking at the security model overall, we also ultimately decided against the secure element, mostly because I think most secure elements are kind of a security theater in a way. So the secure elements that are used in open source products usually are just chips that hold keys secure while the device is offline. So they just hold them secure at rest. But if we have an encrypted flash, we have the same result. So if the secret is in an encrypted flash, it's safe at rest. And when you power it on, you decrypt it, which is the same as when you power on the secure element, it gives you the key. So not all of them, but most of them work this way, especially the open source one, the one that you can use with open source software. And so we ultimately decided, it's just an extra chip. We have a very constrained power limit, and it doesn't really add any extra security. So we decided against it. And then, okay, we have our vision. We decided what to do, what to use. We decided to use NFC. We decided what the security model is. Then what? Well, then it's prototyping. So design the board. We use KiCad or KiCad. It's like an open source tool to design hardware. Maybe not the most advanced, but for very simple boards, it's more than enough. Then you order boards from manufacturers. There are a bunch of really cheap. It's crazy how cheap and accessible it's become now. There are those very cheap manufacturers in China. They make like even 5 pieces, super cheap, and they ship it in I don't know, like a week, in a few days. Then you assemble it. So when you prototype, usually it's much cheaper to assemble them yourself. So you order the parts, order the boards, place the parts on the board, put it in an oven, test the board, and then start again. So there's always going to be something wrong with every iteration, and then you just kind of go through this loop and trying to improve it every time. Luckily, overall we did 4 revisions. So we started with Rev 2A because it was based on a previous unrelated project. So the real first revision was an unrelated project. Then we kind of repurposed it for this, and it became Rev 2A. So that's why it started with 2. And it actually worked on the first try, so we got lucky, I think. But also, it's like a super simple board, so it was kind of hard to screw up. And then the history was, well, in the first revision, I'm going to show pictures later. In the first revision, we had the components on the front side, so we only had everything on one side, the display and then the other components. Then we decided to move the components to the back, with the idea of adding a case to protect the components. So we were like, okay, let's move the components to the back, and then we add a case to the back that protects them. But the case was not. There was no way to mount the case. So then with the next revision, the hardware stayed pretty much the same, but we added like notches so that the case could kind of snap into the board and stay there. And then we realized those notches were not enough to hold everything together, so then we made those kind of notches or those cuts larger so that we could accommodate screws. So now the final revision has 4 screws that all stack together, and we have a back case, board, and a front case. And these are renderings of the various iterations. So started with 2A. This was August 2023. And yeah, this was just kind of the first version, everything on the front. I didn't even have 3D models for like the displays and stuff. So the first version was just that. Then we moved the components to the back, made the board slightly longer so that the button was a bit bigger. Then the next one, I don't know if you can see that there are like notches with 2C. And also we changed the design of the button, or at least the design of the graphics where the button is located. And then finally, revision to the bigger notches. Also, the display is slightly moved. It's centered now, so it was slightly off center, and it was bothering me. So I made it perfectly centered. And now there are the larger notches for the screws. And the last one was in April 2024, so it was almost a year. I mean, like 8 months of iterating and obviously in parallel developing software for this. And I also have the back, which is maybe the more interesting part. So also, I don't know, random differences. So we have time, I can get into that. In the first revision, I was using connectors for the display. So you can see the footprint is for a connector, so the display was not directly soldered to the board. Then starting from the next revision, the problem with the connector was it's kind of thick. So with 2B, we decided we wanted to add a case. So we didn't want the extra thickness, and it's also an extra component, so extra cost. And it's also harder to solder because it's smaller pitch for the pins. So with 2B, we started soldering the display directly. And then the hardware pretty much stayed the same from 2B onward, and it was more like cosmetic changes, so slightly changing the graphics, increasing, so making the notches bigger for the case. And also, I don't know, funny thing, you can also see in the last revision, we had to add, the CE marking and I think it's WEEE, the trash can thing for regulatory purposes. So you can see, like, it started as a prototype, then it became a real product when you add compliance sheet on top of your product. As always, compliance, and we're going to get into compliance later as well. So yeah, this is kind of the whole evolution, simplifying and refining, I would say, the hardware for production. In terms of firmware, so there's so many things we could say about this. The firmware is written in Rust, specifically no STD Rust. So it's like a subset, let's say, of Rust that doesn't use the standard library, or at least, part of the standard libraries are available. But yeah, it's a subset of Rust. So you cannot run regular Rust straight away, but with minor modifications you can. And the firmware is built on Rust Bitcoin and BDK. I forgot to mention before, I'm originally the founder of BDK, where BDK is a library for building Bitcoin wallets in Rust. And BDK stands for Bitcoin Dev Kit. So before doing this, I spent 3 years working on BDK with various grants. And then I was like, I want to build something with BDK. I want to build a product with BDK. So it was also one of the driving forces that pushed me to building this thing, because I wanted to use BDK in a real product. I didn't want to just work on abstract libraries that didn't really have, they did have practical uses, but I wanted to work on the practical uses. So firmware Rust, based on Rust Bitcoin and BDK, with very minor modification. Recently, not so recently anymore, updated to 1.0. So if you know BDK, there was a big deal of BDK 1.0 and lots of things changed. And the really cool thing about the firmware is also that we can update the firmware through NFC. So it's pretty much the firmware as functionality to replace itself in a way, which is cool, but it forces us to halve the capacity of the flash, because we run the flash in a dual bank configuration. So you have one firmware running, and then this firmware running can download a new firmware, and it's going to get written to the other bank. So if something happens, if the firmware is corrupted, if the signature is not valid, whatever, you never switch to the new bank. So you just stay on the previous one. So effectively, the STM32 that we use has 1 megabyte of flash, but we need to halve it for this dual bank thing. So effectively, we have like half a megabyte of capacity, which is plenty. But Rust, especially Rust code, which is not explicitly designed for embedded, tends to blow up quite a bit. So firmware size is a bit of an issue for us. We need to optimize the code, not in terms of performance, but optimizing it in terms of code size, so that we can squeeze more functionality in half a megabyte. And there's also a lot of tricks, things that we had to come up with to make it work. So some examples I put here are, for example, everything is async. So we use async Rust. And usually, like on a desktop, for example, async means when you're not doing anything, you just release the CPU to the system, to the scheduler. And on embedded, there's no scheduler, there's no, it's just bare metal hardware. But what it means, using async, means that when we're not doing anything, we can put the core to sleep. And this helps a lot with the constrained power we have. We also run slightly underclocked core, so we're not using the default, which I don't remember, I think it was 80 megahertz for the CPU. We downclocked it to, I think, 64, again to save a little bit of power. Still plenty fast, so like more than enough. But yeah, we need to be very careful about not having, busy loops, runnings. Everything is async. As soon as we're not doing anything, any computation, we just put the core to sleep, and then we save power. And we charge up. We have a bunch of capacitors that kind of store the charge we accumulate from the NFC. So when we go to sleep, those capacitors get to recharge a little bit, and then when we need them, we get a little bit of power. Also, another really fun thing to do and to debug was, there's this thing on iOS, which is iOS has a hard limit of 60 seconds for NFC interactions. So after 60 seconds, the OS kind of shuts down the communication, and it's still more than enough to transfer the transaction and complete signing and send it back. But there's actually another undocumented limit of 20 seconds for each specific, let's say, transaction, like meaning transaction in terms of data exchange. So instead of extending to the 60 seconds, the OS would actually cut off the communication after only 20 seconds. And that's pretty tight, because you need to upload the transaction, which doesn't take much, but then the user needs to be able to see the address and double check the address, and doing it in 20 seconds, then it starts getting pretty tight. So we figured out a way to disconnect and reconnect very quickly, so that iOS is happy, because iOS sees the new device. After it reconnects, it sees that as a new device. So it restarts this kind of 20-second timer. But this means that we have like effectively a reboot, a very short reboot for like 50-millisecond reboot in our device. So we need to somehow preserve the state. If the user is signing a transaction and they were in the middle of signing, we need to preserve that, power off, power back on 50 milliseconds later, and restart from where we left off. So that we can we do this 3 times to extend the 3 20-second windows to a full 60-second kind of transaction. And yeah, that was obviously very fun, because we need to write like consistently the state. We figured out there are a few registers that preserve the content for like up to a second after power off, after you remove power. So while you're doing things with the device, we constantly write the current state to those registers. So then when we power back on, we can restore the state from those registers. And it was fun to do. Also, we ended up implementing, we forked QEMU, which is like a very popular kind of emulator. It's used, for example, in the Android emulator. It can emulate ARM CPUs from server CPUs all the way down to embedded targets. And they already kind of supported STM32s, so they had like a machine for an STM32 board, but we forked it, we implemented all the peripherals we use, so now we can like fully emulate a full system with peripherals, which is like the display, the NFC chip. Those are all peripherals of the STM32 that we can emulate with our fork of QEMU, so we can pretty much run, in the CI, we just run tests against a fully, as if it was a real device being emulated. And that helps a lot with debugging issues that we see on the real hardware as well. So the hardware is developed, software is developed, now that's it, right? Well, unfortunately, there's everything else. I like to call it everything else because it's the usual 80-20, so the last 20% takes 80% of the time. So developing the hardware and the firmware was probably the quickest part and easiest part. Then there's everything else. So for example, plastic case. I went a little bit into the details before, but we started with no case. Let's just have a bare board. Then we realized, well, people may touch accidentally the pins, maybe short them out, maybe have their hands slightly wet. So then let's move the components to the back and add the case to the back. And then we realized that playing with this and using this, we realized the screen cracks very, very easily. I dropped a few of them, the corner cracks, and it still works, but you lose like odd pixel rows. So you have like one row of pixel working and the other one is dead. So then we started adding a case to the front as well. So we developed, this is why we started adding notches, so that we could kind of merge together the back side and the front side that covers the display. And then the last piece of the puzzle was optimizing the 3D model for injection molding, because obviously for prototyping we were just 3D printing, and then at some point we wanted to scale up production, so we needed to injection mold it. And this is the final design. This is actually the only part that we didn't fully develop in-house, because we contracted with, so we developed the design and everything, but then we contracted with a small company from Scotland called Cramazy, if I remember correctly, and they're like super good guys. I loved working with them, and they kind of helped us, for example, adding the ribs so that we have a consistent thickness, because when you injection mold, you don't want plastic to harden in one place and still be liquid in another. So you want a consistent thickness throughout. And yeah, there's so many things going on. There's also like a sliding window for the piece that kind of protrudes. I don't know how to describe it. So yes, a lot of really cool things. We are finally getting injection molded parts now. So mold is finished. We've done the surface finish and everything, and we've ordered the first batch of injection molded cases, like literally last week, and it took months to get to this point. Other things, packaging, for example. So how do you package? This is a security product, so we want to reassure people that the device doesn't get tampered with or replaced while it's in transit. So what we do now is we package the device in tamper-evident bags. So they're like bags, the bags that you use to ship cash, pretty much. So those are bags with seals that once you open them, they have the void, the pattern, whatever. They're all serialized individually, so they have a big serial number in the front. And we also flash the same serial number into the device. So when you power on the device, it's going to show a serial number which should match the one in the envelope that you received. We also designed a very simple box with like padding inside for protecting the device. And then we needed to figure out a way to keep the box closed. And initially we tried, those round, transparent stickers that you find everywhere. But the ones we got from Amazon probably were terrible. Like they wouldn't stick at all. So then we realized, well, we have a brother label printer, like generic label printer, which we use to print the thing on the right. So the barcode and the serial number. Like, why don't we use the label printer for printing the seal? So actually for every device, we print two labels. One is the actual individual one-of-one label with the serial number that goes on the side. And we also print the other thing, which is the seal that we use to keep the box closed. Obviously, it can be replicated because we're not using any tamper-proof seal, but there's still a tamper-evident envelope within the box. So even if you open the box and replace it, there's still a tamper-evident envelope inside that protects the device. And ultimately, what we're trying to do now, which is complicated, we're working with another logistic partner, but ultimately what we would like to do is when a customer orders a device, we send them the serial number that we are shipping them. So we can tell them, from the factory, this is the serial number that's being shipped. And once you receive it, you can kind of compare it for again, more security. Well, then there's compliance, which is a huge mess. It was probably the most frustrating side to it. So, all the regulations on emissions, on radio, and even figuring out, do we need to do testing of our device or not? Because we use NFC. NFC is not really radio, it's not Wi-Fi, it's not Bluetooth, but it's also radio, kind of. You have antenna. So that was a mess. And for this reason, we're still not shipping to some countries because we're still trying to figure out for every individual country, is this compliant? Obviously, it is compliant, but how do we prove it is compliant? What kind of certification do we need to get? How many thousands of dollars do we need to spend to get that certification? And if it's for a small country, it's just not worth it. So unfortunately, we're not global yet, even though eventually we want to get to that point. But in terms of production, the way we are dealing with it now, we're obviously working with pretty small batches. We're a small company. So we order parts from manufacturers, mostly in China. By parts, I mean like a fully assembled board with components soldered. But we still do the testing of individual boards, the flashing, which is the most sensitive part, and packing everything. We do this in-house. Like, it's literally us, me, my co-founder. So my mother sometimes helps us. She's like retired. Sometimes we need help. She comes help us. So yeah, we are trying to move as much as possible to Italy, as much of the production as possible, especially the boards, because they are slightly more expensive, but you tend to get better quality. But still, ultimately, the most sensitive part, which is flashing the firmware and packing it in the envelope, we do it ourselves. So there's we're not outsourcing that. And maybe at some point we will figure things out when the time comes. And also, another funny thing, we developed a bunch of 3D printed tools to help doing all of this. So for example, we have a 3D printed like jig where you place the board, and there's like a latch that keeps it there so that you can flash. You can hold it there for like 30 seconds while it's flashing. Then we developed another 3D printed thing which holds the full stack of case, board, back case, so you can screw it in easier. So this is kind of a recurring theme of developing tools to help you do your job. And it's also really fun. Sometimes it's physical tools, like 3D printed tools. Sometimes it's software. But yeah, that's also very fun to do. And in terms of logistics, I kind of touched on that before. So we use anonymous packages. Basically means we take the box and we package it in something else. So we ship with DHL for everywhere except Italy and BRT in Italy. And we use DHL generic DHL kind of envelopes for DHL, and we use just random bags for Italy. So basically from the outside you cannot tell it's an hardware wallet, which is good. Another tool we kind of had to develop was again automating kind of label creation. So we have our scripts that take orders from Shopify, they connect to DHL, get the label, print it out. I made this website, which is like a super quick website for printing labels. So we buy A4 sheets with 4 A6 labels on them from Amazon. And so I have this tool where I just kind of drag and drop the labels, and then I print it with a regular printer, and then I can take the labels and stick it on the packages. So right now we're also managing the logistics ourselves. But in progress, we are speaking with a third-party logistic service because now it's starting to get too much. So it's too many things. And logistics is not as sensitive because, again, we have tamper-evident bags and stuff. So the most sensitive part is assembling the device. So we want to do that in-house. Logistic, we can outsource it very easily. So we're speaking with DHL, effectively, for their third-party logistic service. So we just give them the stock and they ship it out to customers. So conclusion, making hardware is fun, as we've seen. It was probably much harder than I expected when I started, but still I would do it again because it was a ton of fun. And all of this, all the engineering was done by myself. So I'm a software engineer pretty much, and I taught myself hardware design over the years, kind of for fun. And I did all of this by myself. So designing the case, designing the board, writing the firmware. So this proves you don't need like a big team, lots of money. This was we haven't raised investments or anything. It was fully funded by ourselves. And I'm working with other people, so I'm not alone in the team, but I'm the only engineer. So I did all the engineering side by myself. So I hope this, can inspire you to do the same. You don't need big teams, you don't need lots of money to get things done. Just stick to it, just dedicate a year of your life to something, and you can make, cool products out of it. I think this is it. I'm happy to take questions if you have any. Otherwise, thank you for coming.
What's the maximum number of UTXOs that you can get through in the limited time?
So I don't have a specific number right now. I could do the math, but it's probably in the tens. Like I would say at least 50 for sure. Obviously we're focusing on average people, like generic people that don't have any special needs. And in our testing, we tested, with wallets, try to simulate regular spending pattern. It was never a problem. Maybe if you have like hundreds of UTXOs to consolidate, then it becomes a problem. But for regular use, it's I think up to 50 easily. Yeah.
Okay. And you said it's available for Android and iOS.
Yeah.
Do you think it will be a big thing to port it to Ubuntu Touch?
To port it on?
Ubuntu Touch?
So yeah, we developed a library that implements all the logic to communicate with the device, which is also in Rust. And then we have bindings for the main mobile platform. So we have like Kotlin, Swift, React Native, and Flutter. But it's trivial to add, Python bindings or whatever. So as long as you have NFC hardware, I also run it. It's not, let's say, officially supported, but for myself, for testing, I also run it on my laptop, actually, with a USB NFC reader. I just run the Rust library straight, like a Rust binary. So you can definitely, you don't really need porting. It's just a matter of you need a device with NFC. You need some library to use this NFC, and then you can take our library, which implements the logic, kind of bridge it together. And we try to make it super simple. So you literally take a row NFC messages straight from the device, give it to our library. Our library tells you, okay, send this back. It's like completely blind. So you only need to implement the actual communication with the device. So yeah, you can probably, I never tried, but you can probably implement it in Ubuntu Touch pretty easily, as long as the device has NFC.
Okay, thanks.
Yeah.
Just a curiosity, why the circular design?
Yeah, so the circular, the round part, maybe I can go back to it. So the round part is the antenna. So in there, in the inner layers of the board, there's the NFC antenna. And it needs to be kind of big because it needs to harvest a lot of power, like relatively a lot of power into power display, microcontroller, and everything. So the round part, I mean, you could make it square. I think I guess I made it round because I liked it round, but you need that kind of big part for the antenna. And then the other part is like the thing that sticks out. So actually, I forgot to bring one here, otherwise I will show you. You tap it against your phone, you have the big antenna against your phone, and then you have the display kind of sticking out. So I also did the design by myself. I'm not a designer, so I'm sure, yeah, in terms of look and probably even industrial kind of design could definitely be improved. But yeah, I liked it round. I guess that's the easy question, easy answer. I forgot to mention, while you think about questions, forgot to mention we have a booth at the Bitcoin Bazaar. So if you go upstairs, we are selling, we have a few units left to sell, but also if you just want to see it in action, if you want to play with it, we're doing demos there. And I'm also going to do a workshop, but that's in Italian, in the thing on the other side of the street. And during the workshop, I plan to just let people play with it. Like you can download the app and play with it on your smartphone. So either if you want to see a demo, go upstairs. If you want to like actually try it, come to the masterclass later, but it's, to the workshop later, but it's going to be in Italian. So yeah. Did you have any question? No? Okay. Sorry, I thought you were raising your hand. Sorry. Okay. I don't know. I think this is it. Thank you so much for coming. See you.